All right. Welcome everyone to another Materialize community meetup. Thanks for taking the time out of your day to join us for this overview of the platform updates in Materialize. So we're going to be talking about the next generation of Materialize. The great unbundling is complete, and Materialize is now a cloud native database. And we're going to use this time to dive into what the heck that means. I'm Andy Hattemer. I'm joined by Joaquin Colacci. He's from the developer experience team. He'll be on hand to help answer questions. So please, if you have questions, ask in the Zoom chat. If you have questions afterwards, you can join our community Slack. There's plenty of Materialize experts and engineers there to help out. Okay, let's get right into this. So we're going to start with some context. We'll talk through the major architectural changes in terms of before and after, and we'll talk through some key concepts in the new architecture and how they're used. And then we'll close with some hints at what's next and plenty of time for Q&A. Before we get into what has changed, let's talk about what is the same. And the fundamental promise of Materialize remains the same: fast, efficient, incremental view maintenance on changing data, all in a SQL database. We still present as Postgres. We're still using ANSI SQL as the query and control language. We still excel at all manner of complex streaming joins. There's a dbt integration, as well as Kafka sources and sinks and Postgres sources. And notably on the company level, all of the source code is still developed in public on GitHub and under the same BSL license that we've always used. In terms of what's new, 4 big things stand out. Materialize is cloud native now. So we only deliver the distributed architecture as a cloud product, similar to something like Snowflake, where you create a Materialize account, the resources are managed by Materialize, et cetera. This was a big decision we made in order to focus on providing the best possible experience for this new unbundled architecture, which is the big one. And that's the second change, where we took what used to be a single binary and separated it out into a distributed set of services. So that's what we'll be talking through today. And a big part of that is that there is now a durable storage layer. So Materialize used to act only as an in-memory engine, and it now durably writes incoming data and even certain types of transformations down into storage. And then lastly, strict serializability. We'll talk more about this later, but it means we were able to provide the same consistency guarantee and correctness guarantees as production-grade databases. And this is notably different than other stream processing products out there. And then just for a last bit of context, I wanted to shed some light on some emergent themes and use cases that we've seen in this early phase. So we've gotten tons of feedback from our preview customers and early adopters. And we notice typically they come from one of 2 camps: the database people and the stream processing people. Camp stream processing is excited about 3 things in this new architecture. So the SQL database abstraction on a stream processing system is a more user-friendly control layer, meaning that they see it as this thing that a broader set of engineers can contribute to and maintain. And projects have a higher success rate, more staying power, and even adoption and growth internally because they're easier to contribute to and they're easier to maintain. The second is, without fail, everyone that has dealt with the current crop of stream processors sees strict serializability and gets really excited because they've had to deal with the endless quirks and caveats and complexity of systems with looser correctness guarantees like eventual consistency. So the promise of strict serializability in Materialize is just that you write SQL and the results are what you would expect. And there's not lots of caveats and edge cases that come up in other stream processing systems. And lastly, they're also excited about being able to use a single service for ingest, processing, and serving. So a lot of other stream processing systems focus on the first 2, but if you want to maintain the state and query it, you need to add another service. For us, the serving part is a key part of the product. This is why we present as Postgres. We're able to generally reduce overall system complexity without compromising on latency or features. And even in this distributed architecture, the query latency is typically in the milliseconds. And then on the database camp, it's a bit more straightforward. People want fast, efficient ways of handling complex, repetitive transformations. And those kinds of transformations typically happen most often in the analytics world, where teams are already using stacks of SQL transformations in a batch warehouse. And what they're finding is they're able to write similarly complex SQL transformations with all sorts of joins and aggregations and take their latency down from 24 hours or 1 hour to sub-second. And they see lots of new opportunities that open up around serving fresh data to internal teams, other systems, and even customers. And then the other thing that the database camp is really excited about is this idea of event-driven or reactive architectures in the database. And what I mean by that is something that other databases have gotten tantalizingly close to. Firebase has concept of subscriptions in it. And if you're familiar with RethinkDB, it was a attempt at a reactive database with subscriptions as a default. And even new databases like Supabase are building limited functionality versions of this. But the general idea is that you're able to end polling or refreshing or requerying your database, and you can build architectures where you just wait for the changes to be pushed to you or to the client from the database. And it turns out when you use a stream processor as the engine for the database, these kinds of things come for free. So we'll talk about some of those concepts with things like sync and subscribe later. And then in terms of use cases, it's really 4 categories that we've seen in the early access. There's real-time analytics. It's always a big starting point. We're seeing both internal teams and SaaS products building segmentation and personalization type of use cases with Materialize. The event-driven features make automation and notifications a common use case. And lastly, we're seeing lots of machine learning use cases where strict serializability is particularly useful. Okay, let's get into the distributed architecture. So before I actually get into it, this quote is perfect for the occasion. I originally saw this on Twitter, but then someone pointed out that, I think Joaquin, you pointed out, it's featured on the first page of our co-founder Frank McSherry's amazing cost paper too. You can have a second computer once you've shown you know how to use the first one. In a way, we've spent the last 2+ years showing we know how to use the first computer. And now that we've done that, we're ready for our second, our third, our fourth, and so on. And here's what that looks like in the old versus new architecture. So the old architecture, the single binary, had all the services in a single process, single machine. This was useful for focusing development on creating a correct and a performant and a user-friendly architecture. But we always knew we'd hit a limit. And so back in April, we decided it was finally time to get our second computer and unbundle into a distributed architecture. So we still present as Postgres. The new architecture is roughly 3 layers. There's the SQL control plane, compute, and storage. And under the hood, it's a horizontally distributed system with separation of compute and storage. The storage lives in S3, or when we expand to the other providers, their own object storage APIs. It's cheap and scalable. And then for getting data in, the streaming sources we'll talk more about allow us to stream data in from Kafka and Postgres. And there's also all of the standard SQL features of a traditional database, like SQL tables, where you can write data via insert and update statements as if it were a regular database. And then in the compute layer, this is where the query engine would typically go in a traditional cloud database, but for us, it's clusters of replicas that handle the indexes and the maintaining of those indexes via Dataflow. So let's talk a little bit more about streaming input sources. Sources they consume streams of data from Kafka and Postgres and immediately write it down to S3. And each source is allocated a dedicated and configurable amount of resources, CPU and memory. So upon creating a source in Materialize, it begins consuming the messages of the available records for that source, timestamping them, which is essential to the way that it operates as a distributed system, and storing them in S3. And the benefits of this architecture are that we can scale the sources and the compute independently of each other. So if you have one really high throughput Kafka topic, we can scale that source up, give it more resources, and lower throughput topics can be allocated minimal resources. The isolation also means that they can fail over independently. So sources are the easiest thing to restart. They're basically stateless, where they just read data from somewhere and they write it down into the storage layer. They're also the most likely thing to fail in practice because they're the ones doing all the network communication, and depending on external services, the isolation from each other and from compute is actually a big advantage over other system designs. Now let's go a little bit deeper on compute. The compute layer handles data flows and in-memory indexes, which in our world are called arrangements. And there are two important concepts here. Clusters are logical components, which are purely a way to group and isolate the work. And replicas are their physical counterpart. And this is where the resources are actually allocated to do the data flow computation and maintain the indexes. Some important features here are that an account can have many independent clusters, and clusters can have one or more replicas. We'll talk more about the replication later. And it's in an active configuration. So there's no primary and secondary. They're all the primary. And replicas scale vertically and horizontally. What that means is the smallest replica can use fractional, just part of a machine, and the largest replica actually spans multiple physical machines. So it can have more resources than the largest EC2 instance, but to a user functions as a single component. And the ways that you actually use the compute are creating indexes. And what that does, it creates the data flow to maintain an index, and then it creates the in-memory index that can be queried or used in other queries. Create materialized view, which we'll get into more detail in a little bit. And then also notably, if you're a user of the binary, this will be interesting to you. We now also answer ad hoc queries. So if Materialize, the SQL adapter layer gets a query that it's never seen before, it will create a temporary or a short-lived data flow to answer that query on a cluster, serve it, and then destroy the data flow. So it really functions like a regular database if you ask it to. You would be missing out on some of the best parts, but it will work that way. Here are some examples of how people are using clusters in the compute layer. So you can separate clusters for development, staging, and production environments. That's a pretty common one. You can set up a cluster to handle the processing of raw data, and then a separate cluster to handle just the last mile joins and serving of that data. I'll talk a little bit more about that in a minute. And then you can also test new workloads on scratch clusters in order to validate use cases or benchmark resources. And you can give generally just kind of isolate workloads where you're able to give separate teams in your organization, separate clusters, and isolate things that way. So if one cluster fails, it has no effect on the others, but they all have access to the common storage layer. And then this, I'm calling it a new capability, even though it's what we've always had in our namesake, materialized views, but it's new because we made a fundamental change to how materialized views work between the binary and the new architecture. And in short, we're basically writing materialized views down to storage instead of maintaining them in memory. So materialized views, when you create materialized view, you are creating a data flow in the compute layer to do the computation, but the rows, the end results, instead of being in an index in memory, they're written down into storage. And that provides a bunch of really interesting new use cases. Some of these our preview customers have come up with, and there's probably many more that we haven't even thought of yet, but here are a few that definitely have emerged. Generally, the most obvious one is just this optimization of resource usage, where you can now choose, do I want the final state of this view to be maintained in memory or written down to storage? And it's a trade-off where in-memory is more expensive, but the query latency is lower. And in storage adds latency, but it's cheaper, and it means that the results can be shared out to other compute clusters. So it creates capabilities like increased resiliency to upstream failure. And this is that same separation of processing and serving that I mentioned earlier, where the way it works is you have your first cluster dedicated to the kind of the dirty work of processing, aggregating, doing computations, and all of the results of maybe multiple views and indexes are written back down to storage as materialized views. And you have a second cluster with much simpler views and indexes that is 100% dedicated to doing the last mile joins and serving. And what does that give you? If you think about it, if your DBA in the upstream database that you're pulling into Materialize makes a big schema change that causes a breakage in your dirty work of processing and aggregating in that first cluster, what will happen is it will stop updating the materialized view in storage. And so from the user perspective, you've basically just chosen, or the serving layer continues to serve the results. They're just stale results. So you've chosen, I would rather serve stale results than no results at all. So it's not always a useful scenario, but in a lot of cases it is. And the important thing is it's a choice that you can make as a user, where before you weren't able to even have a choice. And then one last example use case to call out is kind of a buzzwordy thing, but it's actually particularly useful for materialized views. This idea of data mesh, where if you have multiple teams in your org or in your business who are operating on data and Materialize, you can have different work that you're doing purely in your cluster, and you can have work that you intend to be shared in public written down to storage as a materialized view. And so the difference there is other teams, like an analyst team, can read from the materialized view, and you're basically now, org has control over the dimensions or the views that they expose to be shared and joined amongst the larger business. And it creates some nice separation of responsibilities. Let's talk more about replication and what capabilities that opens up. So as I mentioned before, Materialize uses active replication. Each cluster replica is a clone, and replicas receive a copy of all the incoming data, and they perform identical computations. So creation and destruction of replicas is done without any impact to serving, even in the case of open transactions like subscriptions, and queries are routed to all the replicas from the SQL control layer, and results are served from the first to respond. And then lastly, replicas can be different sizes within a cluster, and we'll get into why that's useful next. So the benefits of replication are some of the obvious ones, like increased resiliency to failure and high concurrency or reduced P99 latency, but also with the ability to create different sized replicas and create and destroy them without user seeing anything. It enables scaling up and down, where if you see that a replica is starting to strain under the compute load, you can create a new larger replica, and once it's safe, destroy the undersized replica with no noticeable impact to the end users. Replication is also key to enabling zero downtime version upgrades in the future, where you can imagine a replica with an updated version of Materialize can be started. Once it's verified as operational, the old replica can be destroyed. Sync and subscribe are two ways of getting data out of Materialize that are slightly different in the new architecture, so I'll talk about these. So these are essentially ways of getting a stream of changes or results, or a stream of changes to results or views out of Materialize. Subscribe takes it through the SQL interface at the top and serves changes out in the form of a long-lived transaction that works with all standard Postgres drivers. And a subscribe connection, as I mentioned, can survive all of these replica create and destroys happening below the surface. And syncs are taking that same stream of changes out from the storage layer, basically, where you can kind of think of them as a counterpart to sources. They're isolated from compute, they're isolated from each other, and they're producing streams of events to Kafka. Each sync can be sized based on the throughput, just like sources. Syncs produce exactly once semantics by default and can survive failures and restarts without losing track of progress now. Some of the sync and subscribe use cases that we're seeing there's really interesting continuous testing and monitoring use case where you write a view that should never return results and treat new rows that appear as error alerts. So if you're using the sync, you're monitoring Kafka, a particular Kafka topic for events and acting on those in whatever way you want. Or you can also have a long-lived Postgres connection that's subscribing to changes and taking action when it sees an update. There's also lots of other event-driven push-style use cases like notifications, automation, other types of alerts, and more generally, some really interesting new event-driven architectures. Subscribe, in particular, enables an architecture where each connected client is opening a long-lived subscribe connection and efficiently getting pushed just the updates instead of polling or not updating at all until a refresh. So I think there's some really interesting new architectures that can be built with the subscribe and sync semantics. Okay, that was a lot, but we've got even more coming. We're still in early access, but we've used the preview customer feedback to prioritize certain features like source security, where shipping more methods of securely connecting to an upstream Kafka or Postgres source. We also have a major update to the Postgres source that we call Postgres demuxing, where instead of taking in the raw logical log feed of changes and kind of leaving it up to the user to decode and parse, we actually recreate the schema of your upstream Postgres database as views in Materialize. So you can immediately begin building new transformations, almost as if it were a Postgres re-replica. And then something particularly exciting that actually Joaquin was a key contributor on is the Materialize CLI, which is a command line interface for authing and managing and configuring Materialize, where the majority of the interaction still happens in a SQL shell, but this just gives a much better user experience around all of the workflows that lead up to the SQL session. And then some preemptive FAQs for access. We're just wrapping up a private preview period where we've gotten a lot of feedback from our preview participants, and we're going into early access. You can register at materialize.com/register. We'll be in touch about setting up access. Pricing, how that works is accounts are billed in compute credits based on the compute resource hours used. So the cluster replicas, that's actually a typo. I wrote clusters, but it's cluster replicas, sources and sinks, and all use compute credits at a rate based on their size, and storage and network is a pass-through charge. So with that, any questions folks have, we'd be happy to answer now, or we can always follow up in the Slack. And don't forget to get on the early access list, materialize.com/register. Looks like Damien asked if we plan to support other clouds. Yes, definitely. We don't have a timeline yet, but Azure and GCP are definitely in the roadmap, and we're building things with the intention of making that a pretty easy expansion.
I can answer the second question related to the replicas and how does the balancing works. All the queries goes to all the replicas. We retrieve the faster answer and share that answer to the client.
Right. That's actually a good one. Yeah, that's why your P99 latency goes down with multiple replicas. Matt asked about strict serializability and mind sharing more about the use case or functionality. So let me give a basic example. When it's most relevant when you are pulling in the change feed that's originally coming from a database. So if you're using the Postgres connection or the Postgres source, or the Kafka, where you maybe are using Debezium to get your change feed into Kafka and then pulling that into Materialize, you end up with something where in your upstream database, there might be transactions where a single transaction might be updating multiple rows or making multiple changes, and it's produced to the change feed or the event log as multiple events. And if you didn't have strict serializability and you only had eventual consistency, as most of these other systems have, you would be potentially serving half complete results where your streaming system processes the first 3 of 6 updates in a single transaction as individual messages and produces a result that should never exist, or it's incorrect. And the timestamping process at the source level in Materialize ensures that through all of the data flows and results serving, we're never serving incomplete results that way. So if we've processed the result, or we've processed the event from part of a transaction, we're not going to serve a result until we've processed the results or the events from all of the events from that transaction. And that's something that's built into the underlying system that Materialize is built on, differential data flow and timely data flow.
Yeah, I went to add that also is useful when you're handling tables, transactions with Materialize cursors or different stuff. It's also useful.
We've got a couple more questions here. do you have option or plans to provide platform as a service with security features like SOC 2? That's interesting. We're definitely it would call it more of an infrastructure as a service, or, database as a service, where the user, we are not focusing on providing like a web UI for, analyzing the results and things like that. We kind of expect the user to bring their own tools, and that's part of the Postgres compatibility. SOC 2 compliance, I think I don't know if I'm allowed to say officially, but it's in the works at a product level, unrelated to the like platform as a service question. Joaquin, do you want to take that next one about 2 identical size replicas?
Yes, in that case, if you get more and more queries and you start to notice that there are some delays, yeah, probably what you need to do is to create a bigger one, and that should fix the issue. If that keeps to be the problem, yeah, increasing the size of the should be the answer to that.
And then this last question.
That?
Oh, what's that, Joaquin?
Yeah, there is another question I was going to answer. The last one.
Yeah, if you can read it aloud too, just so we have it on video too.
Yes, let's see if I can. So their issues, their failure areas will look like with object storage instead of memory. So when you're having an issue with Materialize, and for example, something fails, if you have the replicas, then it's going to be no issue. It's going to keep running. The replicas are going to get up, consume all the information again, and keep working. The good thing is that since everything is stored in Materialize in S3, the way to recover, the speed to recover from that issue is going to be a lot more faster than sending the request over the network to the source again. So the way to recover from a failure is going to be faster. If you are using Materialize and then a query is consuming tons of memory, of course, it's going to fail. It's going to recover, but that can cause that a replica can go down because it's an overflow. But besides that, it's going to be the same.
Yeah, and another, like, the decision to take data from Kafka and immediately write it down into S3 means that if you have an upsert source or a source where it's not append only, when you create a new replica, or even just when you create a new materialized view or an index, you're not having to go back through the history of that Kafka topic, or you're not having to go back to the Kafka topic at all. You're just taking the latest state that's stored in S3 and booting up fast, booting the data flow and the computation up fast with that. So it's generally much faster for new use cases than the previous architecture. Okay, I think that might be all the questions. If you have more, jump in the Slack. You can get there, materialize.com/s/chat, and we'll be happy to answer them. And thanks again for your time today, and have a great rest of your week. Bye, everyone.